We're going to continue our discussion of algorithms to compute eigenvalues. I want to first talk a little bit more about the power method and then go on to some other things. So we had an n by n matrix, and the idea was we took a random vector v, and then we hoped that if we took a to the k v and higher powers of a, that we would approach the eigenvector with the largest eigenvalue, and that would be a way of figuring out both the largest eigenvalue and its corresponding eigenvector. And the idea was, in the special case, if we had n linearly independent eigenvectors, then if we could write our arbitrary vector as a linear combination of them. And then if we compute a to the k v, what we get is lambda 1 to the k v1 and lambda up to ... lambda to the n k to the k vn. And if we normalize it by dividing by the first eigenvalue, we get c1 v1 plus the second term has a lambda 2 over lambda 1 to the k in it, and so on. And then the nice thing is that since lambda 1 is the biggest, all of these terms are going to be going to 0. And we'll be approaching v1, or a multiple of v1. Now the problem is that if lambda 2, for example, over lambda 1 is close to 1, it's less than 1 by assumption, but if it's close to 1, then it only goes to 0 rather slowly. So for example, if it was 0.95, if you raise this to a higher and higher power, it goes to 0, but it takes a darn long time. So the convergence isn't very good. Now what's even worse than that is if, for example, you had the two eigenvalues with the same absolute value, then when you did this, what you would get would be c1 v1 plus the second term would be lambda 2 over lambda 1 to the k times v2, and this lambda 2 over lambda 1 would have absolute value 1. And when you raise a number of absolute value 1 to a high power, it doesn't get any closer to 0. And so this doesn't work at all in that case. So this is a nice elementary method, but its convergence is slow and it only gives you the largest eigenvalue, and so it's not so great. And here's just one more illustration of what I'm talking about. Suppose your matrix was already diagonalized. Well, maybe you didn't know that, but suppose it was, and you just picked the vector 1, 1 to try and find the first eigenvalue. When you compute a to the n times this vector and divide by lambda 1 to the n, well, that's 1. What you get is this vector 1 and 0.99 to the k. And sure enough, that's converging to 1, 0, but you're going to get very impatient waiting for that to happen. Okay, so we're going to move on to another idea, which is that of householder matrices. Sorry for the jump in the slide here. The idea is that computing various things like high powers of a matrix is much easier if the matrix has a lot of zeros. And so we're going to replace A with a similar matrix which has a lot of zeros. Now, you have to be a little bit careful here. You don't want to replace A with another matrix if that other matrix has very big or very small entries compared to A itself. That can really mess up your calculations and errors, and especially if you're doing this thing repeatedly, you can wind up with numbers which blow up. And so the idea is don't use any S, but only use an orthogonal S. And the reason is, remember that an orthogonal matrix preserves lengths. And as a result, it's not going to change the size of the entries of your matrix A very much. So the idea is going to be, given a matrix A, find an orthogonal matrix Q such that Q inverse AQ has more zeros. And maybe you can repeat this and get more and more zeros if you're lucky. So here's the idea. Suppose you have a vector a1 through an. What this comes down to is I want to find an orthogonal matrix Q, which has the following property. When you apply Q to V, you get a matrix where all of the coordinates are 0 except for the first one. Or in other words, it's an orthogonal matrix which takes your matrix V to a matrix in the first axis, axis number 1. And the reason that this is useful is if this V is the first column of a matrix, when you multiply on the left by this Q, you're going to get all these zeros. And so multiplying on the left will give you a bunch of zeros, and then you can repeat this. Now, I talked about doing QA, Q inverse, so you can't just multiply on the left always. You actually need to multiply on both sides. But let's not worry about that for now. Let's just try multiplying on the one side and getting some zeros. Okay, so here's the question. How do you find a Q which takes A1 through AN to something where all of the coordinates are 0 except for the first one, and say the first one is C? Well, my first question is, what is C? So how are you going to figure out what C is? Well, remember, Q is orthogonal. So it preserves lengths. And the length of this first vector is the sum of the squares, and the length of the second is C squared. So right away you know what C has to be. It has to be the square root of A1 squared through AN squared, or maybe plus or minus. So here's the picture. I'll just draw it in 2 dimensions. You have this vector, AB, I'll call it, and I'm looking for an orthogonal transformation which takes you to the x-axis, and we either have to go to this number, 0, or minus it, 0. So I'd like to find an orthogonal transformation which does that. And the key point is what's a very simple example of an orthogonal transformation? We haven't really talked about this too much. I've mentioned it a few times, but I haven't emphasized it. The point is that reflections are orthogonal. If you take a reflection in a plane, that's an orthogonal transformation. The picture is you have a plane, in this case a line, you have a vector, and you reflect it onto the other side of that plane. And that's clearly a length-preserving operation. And remember, length-preserving means orthogonal, so that's a simple example of an orthogonal transformation. And reflections are elementary and easy to compute, so let's find one that takes this matrix to the x-axis, and I've drawn a plane here which does it. If you take this plane roughly, then you reflect this vector in the plane, you get down to this point on the x-axis. So at least in the picture it's clear that you can do this. So let's see, how do we do that? And I need a little bit of a digression here. How do you compute these reflections that I'm talking about? So the idea is you have a single vector W, and that's been given, and it defines a plane, sometimes called a hyperplane, of dimension 1 less than the dimension of your vector space. You take all the vectors orthogonal to W. And the reflection in that plane is what? Well, it's supposed to be the thing which takes W to minus W, because that's what orthogonal reflection does. And it also takes any vector in the plane, in the mirror, so to speak, to itself. And those two kinds of vectors span the whole space. So here's what you do. You take the transformation applied to a vector is given by this formula. It takes V to V minus this multiple of W. So let's see why that's true. The formula is given here, and let's check. T takes W itself to W minus 2 W over W, excuse me, and you cancel those and you get W minus 2W is minus W. And on the other hand, if V is in the plane orthogonal to W, it takes V to V minus 0, which is to say V. And those two properties are exactly the definition of this reflection, so that's the right formula. Okay, let's go back to our picture. So we have our axes and our vector V, and we're going to be mapping it to this point down here in the negative x-axis given here. And that's going to be obtained by taking the orthogonal reflection through this plane, which takes v down to that point. And this is a right angle. So let's see how that works. Suppose we're given any vector v. Then I'm going to let z be the unit vector in the x-axis. And I'm going to let c be the length of the vector. And here's the key thing. You take w to be v plus c times z. And here's the picture. Here's v. And then you're adding some multiple of the vector in the one direction. That's z to get v plus c times z. And then when you do reflection through this plane, that does what you want. It takes the vector v to a point on the x-axis. The claim is that the formula is v given here. This is the formula for the reflection, and we're using w is v plus c times z. So I'm going to plug that in everywhere I see w. And I'm going to check that this does the right thing. So plug that in everywhere. And let's compute this this ratio of squared lengths. So it's v minus 2 times what? Well, you get vv, and you also get a term of 2cvz. Sorry, I dropped the c. And then the denominator, you get vv plus 2cvz, and plus another term, which is, let's see, c squared times zz. Well, zz is 1, so I can get rid of that. And let's see. So that's 1. Now the numerator, I have a 2vcz. Those two terms are the same. Here I have a 2vv, and in the denominator I have these two terms. So I'm taking c squared to be vv. That's what I said to do. And if you do that, then, sorry, it dropped off the bottom of the screen here. This term, the denominator turns into, you get, the numerator is 2vv plus 2vcz. And the numerator, those two terms combine to give you 2vv plus 2vcz. That is to say, the same thing. And it's all multiplied by this vector v plus cz. And this whole thing is 1, thank goodness. And when you subtract these things, you get v minus v plus cz. And the v's cancel, and you get minus cz. And that's exactly what I wanted. So that conforms with the picture that I drew before. This reflection takes you to the x-axis. Okay, so here's a little terminology. The reflection in the plane orthogonal to a vector w is called a householder transformation. It's kind of a long name for a simple object. It's written H for householder, and the formula is given here for the umpteenth time. That's the reflection through the plane perpendicular to W. And the matrix of it is this. It's the identity minus 2 WW transpose over the length of W squared. W is a column vector here, so WW transpose is a matrix. So this whole thing is an n by n matrix. Okay, so that's a householder transformation and a householder matrix. And now we're going to apply this to our situation. We have this matrix A, and the first column I've written A1 through AN. Let W be the vector A1 through AN, and H be the corresponding householder matrix or transformation. So if I multiply A on the left by H, I replace the first column with a new column where all of the terms except for the first are 0, which accomplishes the kind of thing that I wanted to do. Okay, let's now finally get back to our application to computing eigenvalues. So I'm going to start this by talking about a new kind of matrix. Matrix is said to be in Hessenberg form if it looks as follows. It has some diagonal entries, and then the one diagonal just below the main diagonal is allowed to have some entries, and then everything else below the main diagonal is 0. So it's upper triangular with an additional one further diagonal, which is allowed to be non-zero, the subdiagonal. So this is almost upper triangular, but not quite. Okay, so now one can always find an orthogonal matrix Q, which will put your matrix A in this form. And, well, the key point is that you can always easily see how to do this using just these householder matrices. So in other words, it's easy to put A into this form. And the idea is you start with your matrix and you multiply it on the left by H and on the right by H inverse, and what happens? Well, you choose H to get a bunch of zeros like this, and after your first step, you have 2 non-zero terms in the first column. And then you repeat this with the remaining columns. And the way I chose this first H at the first step was the one which I'm only looking at A2 through AN, which kills all of the rest of the terms in this. And so this is an n by 1 by n minus 1 by n minus 1 matrix. So the obvious question you're asking is, why couldn't I get it to be like this? Well, the problem is if I chose H to make A look like this, I still have to multiply on the right by H inverse. And the problem is the H inverse is going to kill some of those zeros. So that fills in a point I was talking about earlier. Using H on the left, I can get n minus 1 zeros, but I also have to apply H on the right. But it turns out that you can get away with it if you allow 2 non-zero terms. So let's see why that is. So I'm starting with this matrix A1. I'm going to just do the 3 by 3 case. I have A1, 2, and A3. And I'm going to use a 2 by 2 householder matrix to kill off this A3. So this is this H inverse. So the H on the left is just acting on this 2 vector with 2 components, and it's killing off the last component to give me a 0. Okay. Now I need to see that the H on the right doesn't mess anything up. So I now have some matrix which looks like this, and I'm going to multiply it by some matrix which looks like this. And I don't care what I get, except that in the lower left-hand corner, I'm getting 0. So that's what I needed to show. With H on both sides, I can arrange to kill off n minus 2 terms. So that gives you the algorithm. You kill off n minus 2 terms first using some H, and then you proceed to the second column, and it doesn't affect the first column, and you kill off the last n minus 3 in the second column, and so on. And after n minus 2 steps, you will be in the form which I asked for, which is to say the only lower triangular part is the subdiagonal. So if you write that out, if you multiply these matrices in reverse order and apply them to A, well, then this product is orthogonal, and Q inverse is in Hessenberg form. And that's an elementary computation. It's pretty fast and pretty easy to describe. You don't have to compute eigenvalues or eigenvectors or anything. So the idea is that we're going to use this to pre-process our matrix A. We're going to give it lots of zeros to start with and then worry about it. Now, an important point is if A is symmetric, then so is QA Q inverse, because Q inverse is the same as Q transpose. And so in that case, being in Hessenberg form, well, it's symmetric, so it's in what's called tridiagonal form. And that's because you only have the subdiagonal below the diagonal, and that means you only have the superdiagonal above it, which is to say you have these three diagonal things can be non-zero, but everything else is zero. That's called tridiagonal form. Okay, now here's another related application. I'm actually going to combine these two. It's the following. So remember the QR decomposition where Q is orthogonal and R is upper triangular? If you don't, go back and remind yourselves about this. And we now have an algorithm for doing this, which is we just use AH on the left. And as I was saying before, if you're only acting on the left, you can kill off all but the diagonal terms. In the first column, you can kill off all but the first one, and so on. And so if you're only acting on the left, you can do better. You can multiply by a bunch of householder guys on the left times A and kill off everything below the diagonal, and that is to say it will be upper triangular, and the product of these H's is Q. And so A is equal to Q inverse R. So that's a nice algorithm for the QR decomposition. All right, let's put this all together. There's something called the QR algorithm for computing eigenvalues. It's extremely slick. Here's what you do. So you take your matrix A and you compute the QR decomposition. And let's say you use the householder thing I just showed you for that. And now you do this clever trick. You let A1 be RQ. You simply switch the order of Q and R. Now, it turns out this is similar to A because Q inverse AQ is Q inverse QRQ. You cancel those, and that's RQ. So RQ and QR are similar, so it's okay. I haven't changed anything. And now repeat. Find the QR decomposition of A1. Well, that's going to be something new. And then switch the order and do it again and again and again. This is an iterative process. And the remarkable thing is that this thing becomes closer and closer to a triangular matrix, usually, almost always, in fact. These matrices become triangular, and the diagonal entries become closer and closer to the eigenvalues. So finally, there's an improvement of this which uses householder in two different places, which is do what I said before. Use this pre-processing of A to put it in Hessenberger form. And that's got lots of zeros. And now this algorithm that I just said, where you do the QR and switch the order and so on, the QR algorithm proceeds very quickly. All right, that's plenty for today. I'll see you in class.